Welcome back to the teaching series on the per unit method. For those of you who have been following us closely, you may have been wondering if we've taken some time off or something like that from our last video. It seems as though our production rate has slowed. Well, it's not the case at all. What we're having a difficulty in is teaching the per unit in a linear, direct way. It just doesn't really seem possible, so we've been really struggling on the way to present these materials. So we feel like a juggler. We're going to present you with sort of a scatter shot of different subject matters. We're going to throw basically these subjects in the air that may not necessarily be directly connected, but once it's all done, you'll see the method to all of this madness. So, we have had a video on where the per unit method applies, and this video we're going to be talking about choosing bases. Other videos we're going to be talking about specific applications and other elements, but they're all just going to be have to be thrown up there, and then once it all is done, we're going to see how it all works together. So like I said, this video now is going to be on the per unit method in its relation to the selection of bases. In our introductory video, the previous video, we discussed the difficulty produced by the turns ratio. If you recall, lots of ends were propagated simply by adding one transformer to an otherwise relatively simple circuit analysis. So we needed to work on how to deal with that added complexity, and we're going to look at the very first principle for removing these ends, which is the selection of base values for your per unit method. The selection of base values of power and voltage, those are two very important bases to consider, power and voltage, is made in order to reduce the amount of work in calculations as much as possible. The choosing of a base is a significant and pretty difficult element actually in the per unit method. On the PE, often the choosing is done for you, or you have a limited amount of choices to make. And most people taught the per unit method are told that they have many choices and a broad range of options to employ while doing it. But keep in mind, for a 6-minute PE specific problem, you'll be forced into making choices which obviously yield the specifics of the correct multiple choice option. They're going to need to pigeonhole you to make sure that you get the answer that is represented in your multiple choice options. And this is very difficult for engineers to deal with, because when they're taking the PE, they walk in with this idea that the per unit method is this really choice-rich, super flexible method which can be applied in many different ways, all of which yielding the correct answer. But really, once you're actually in the test and being given specific values to use in specific places in your calculation, this flexibility feels to go away, and we are left sort of confused by that whole thing. How could this very flexible method now be employed when we're reduced in our flexibility? What this means really to the studying engineer for the PE is you need to not only know how to employ the per unit method generally, but you also need to know how to employ it the way they tell you to employ it for the PE. The PE is going to sort of force you into doing this method in a particular way, and you have to understand the choices they have made, the PE has made on your behalf. So even though this is a choice-based method, especially as it relates to the bases and so forth, oftentimes those choices are going to be made for you. So then, we ask ourselves the very obvious question, what is a base? Bases are used to transform the actual circuit or system values into the per unit values. So they're used as a conversion process to get us from the real world into the per unit world, if you will. There are only four types of bases, which really, those four cover all of the essentials. These four are, very simply, voltage, current, impedance, and power. Now, as far as the method is concerned, that is the per unit method, no base is really more important than any other, but we'll see very clearly that the bases voltage and power are really the preeminent ones in the use of the per unit method, especially as we see it for PE style questions. Voltage and power are going to hold the dominant role. But realize that's not because of the method, it's just because of the practice. The bases also, it's important to know that they come in a variety of notations. Now, these different notations may make you feel like there are more than 4 types of bases. But really, if you take a look at the notations, they're really just variations on the 4 primary bases. So here, if you see, power can be shown in these particular types of notations. Here, with a kVA or an MVA or what have you, voltage is the same. You can see here. So let's list some of the factors for considering bases. So our factors for bases are, there are 4 bases, like we've said: voltage, current, impedance, and power. You have to pick 2 bases, which means the other 2 bases are derived from the 2 you've selected. And most likely, voltage and power are going to be the 2 bases you will select. And that means you will derive the current and impedance from these. Let's consider the circuit we had before in our previous video and see how these particular bases apply. Now visualize the circuit as segmented by the transformers. I'm going to create brackets here, so you should sort of see it broken up into 2 chunks. Once you've segmented the circuit, each of those sections now, those segments, need to have the correct bases selected for that particular section. So you've sort of broken it up into sections, and now there are bases for the sections. Now, what seems to be like an exception to this exact thing seems to come up immediately, which is when you think about power and the conservation of energy. It's possible to have a bifurcated circuit like this, a circuit broken up now into 2 different sections, but actually have the power be the same throughout. In relatively ideal conditions, we can understand that a power base set for this could actually be just one for both sections. We could very easily understand and imagine voltage, current, and impedance changing, but power isn't really altered by the conversion at the transformer. We have voltage changing or some other factor, but power can be the same on both sides of the transformer. Now, moving to the discussion of voltage, we can obviously understand that a transformer is going to affect voltage, so our voltage on one side is not going to be the same as the other side. This means we'll have 2 voltage bases, one on one side, one on the other. And we know formulaically, the V equals IR sort of formulas, that current and impedance are sort of derived from or are composite of voltage. So we can see that those bases will be just as likely to be altered or changed in some way, just like the voltage will be once it passes from one section of the circuit on one side of the transformer to the other. That's why you can derive the other 2 by means of calculations. P equals VI and V equals IZ here are ways that you can calculate bases after you've selected the 2 that you want to work with. Now, we've said that the 2 most likely bases you're going to be selecting are power and voltage. We've shown here that power has a unique characteristic in that it can be applied across an entire system regardless of the transformer in that sense. Voltage also has sort of a unique characteristic, and this unique characteristic ties into the very beginning of our video, which is how do we get rid of these ends up here? How do we handle the turns ratios, which complicate our calculations because of the transformer? Well, you're free to pick whatever base values you want to assign, really, but the smart engineer is going to pick base voltage values that at least match the ratios of the ends. So when you're picking your voltage bases, if you apply the base, that value that is found in the ends ratio here, you'll see that this part up here, where they occur in the formula up here, will actually turn into 1s. They'll end up equaling out to 1, which mathematically we all know makes them disappear. Now, if you recall, that is the main point of the per unit method that we're talking about at this point. How do we get rid of these complicated ends and the turns ratios that are created? We do that by applying this ratio to the base voltage. So let's say you had a turns ratio that was 3:2. This means if you selected your first voltage base to be, for example, 150 volts, and your second voltage base to be 100 volts, you would match this ratio. And the positive effect would be that these ends in the equation above will turn to ones and mathematically disappear. We're not going to show the actual mathematical derivation that turn these turns ratios into one. It's a long process that would require its own video, so you can sort of just take our word for that. There are other material out there which discusses this. What's important to understand and what we're accomplishing here is each section of a circuit which is divided by a transformer, we're, in a sense, taking a relationship and applying it to the base. We're taking this ratio relationship that we find in the turns ratio and applying it to each section. And when we apply that relationship to the voltage bases, that means we can get rid of our turns ratio complications. We're building it in, essentially, to the voltage base. In the next video, we're going to talk about the per unit formulas associated with the bases. And we've seen in this video that the complication created by the transformer in making these ends in our formulas can be removed by the proper application of voltage base selection and its correspondence to that ratio relationship established in